Welcome everyone, thanks for tuning in to another live stream here with FPGA goodness, obviously. And if you're a recurring viewer, you probably know already that work here with Aston's 1-bit squared icebreaker FPGA board stuff here with open source uses, open source synthesis workflow stuff here and Verilog and so on. And we have already previously not only, well, obviously unboxed and taken a look and played around and getting started, and among doing a video core with FPGA-like stuff, integrating this with the RISC-V Pico RISC-V, PicoSoc. And today, of course, we want to add audio. I said this before, except keyboard and mouse, but audio certainly is quite some fun, as you can see. And I wanted to share some design details, or anyway, how I work on this, or how someone could work on this. Welcome everyone, thanks for asking. How are you all doing? I hope you're all doing fine. And thanks for tuning in. So how would you connect this here to the board? We have obviously some I/O pins. We have already the HDMI, DVI stuff running here. And to have here some sound, of course, we can start with some beeping, but how to get this out of there, right? We have only some logic gates, so certainly we need to design our own sound card or whatever. So, of course, one thing you could do is do this here the professional way of doing I2S, the inter-IC sound that I already worked with 20 years ago. Previous video, I sold out my own super high-end audiophile sound card 20 years ago from some CT magazine article, previous video somewhere, Romeo and Julia, CT magazine stuff. And of course I have it here, so theoretically what this means, I2S here is having some clock, obviously as per usual, so this is a serial protocol, and that you can also probably see in this other video. So we have some clock, and that we generate with just some clocking signal, and word select means left and right. So for stereo you would have, like for example, starting with 0, for example, low to have left, and then clock here all the bits like 1, 2, 3, 4, 16, 18, 24, 32 bits. They have audiophile goodness, and then when this goes high for the right channel and so left and right, vice versa, as you can see here. Of course this would work, and that is actually not too difficult, but that would mean we need to have a second integrated circuit. And so I actually have some in stock, so I could take here from my shelf, there's this DIY audiophile board, or actually I have two high-end ICs in stock, but they even need additional components like 10, 20, some capacitors, resistors and stuff. So also to keep this component cost down and for you to learn the most, I thought maybe we do this another month. For today, let's do this direct stream digital, similar to, I actually said this before, similar to what you would have on a, which is a, also wrong camera scene. So it's similar to what you have on a Super Audio CD. This is here, Super Audio CD hybrid stuff for PS3, reversing also sometimes soon because I want to rip them here for backups. So this is some hybrid Super Audio CD, and this means, I said this probably in a previous video, CDs are PCM encoded, which actually I could have opened, PCM, Wikipedia. And so pulse code modulation is what you usually use. This means you have some sample here, and in some sampling rate of, for audiophile CD goodness, 44.1 kilohertz, have here the samples, and certainly can reconstruct any waveform up to a frequency of half the sampling frequency with this Nyquist theorem there, and that is how we usually would do it. However, somehow the people from Super Audio CD goodness thought it's a good idea to, well, reinvent the wheel a little bit. So they have done here what was direct stream digital, and that is what I want to use here. This basically, so somehow they say it is more amazing, but this is of course audiophile nonsense, probably something that deserves another video, because on the wide scale here, from on the view from above, so you see a PCM as we've seen here, and this direct stream digital is pulse width modulating is a signal, and they say that is superior. I call this audiophile bullshit, but whatever. And what this is how internally delta sigma digital analog converters work internally in any way. So for us this means, of course, this is super simple to do, right? We have here an FPGA, we have here some clock, like the base clock of our system here right now is 12 megahertz. Of course you could use whatever else, but given we have here some clock frequency and we have something to output, here, right, something to output, that we certainly can turn the bits on and off and build ourselves here poor humans 1-bit digital, direct, what the heck was it even, direct, I forgot it already, direct stream digital, so direct stream digital here, live on a couple of euro or dollar FPGA. So ironically, so of course, I mean, there you see this audiophile bullshit, but again, maybe I should make a dedicated video. You see the signal to be reconstructed here certainly is the same. On PCM you have here, for example, 16-bit or nowadays 18, 20, 24, or sometimes even 32 for some good audiophile vaporware. And you see a direct stream digital is 1-bit, exactly what we have, right? We have a ground and signal like 1.835 volt, whatever generation of digital circuitry you have there. And so how this works is actually, and by the way, there you see this audiophile bullshit of that is better. I mean, at the end it's generating the whole signal as the same signal, and an identical signal will sound identical, so whatever. But for us it means it's super simple, right? So we don't have an, if you don't have a digital analog converter, you can, like this, build it yourselves. And how this works is, so the more high signal peak value you want to have, the more you turn your output signal on, and the least you want to have it, the less you turn it off. So for example, if this is your ground and this is your 1 or 5 volt, if you wanted 0 volt, you just have it off, and the more you want the signal on, the more you turn it on, and for everything in between you multiplex there, pulse width modulator in between. Super totally simple, and the cheapest form of this actually, if you don't, of course the audiophile stuff is doing this in some separated integrated circuit, but the poor humans form of this is simply to pass this high frequency value here through some low pass filter with some resistor and capacitor that we will do tomorrow or something of that sort, and filter all this high frequency noise that is ultrasonic harmonics anyway, and you will not hear, but so smooth out the signal through some low pass filter with in the cheapest form or a capacitor resistor, and that's it. I actually checked today, comments in the audience posting links. Links should work. I thought I just accidentally checked it today. Links should work, but if you post, someone like administrator, admin, or myself can approve it. So let's work on this. Also, by the way, ironically, this is how in the 80s, if you had some bloody not fun like Amiga 500 boring IBM PC with a PC speaker that ironically with a direct stream digital for audiophile super audiophile goodness. This is ironically exactly how this digital audio conversion on a PC speaker worked, just that you couldn't like nicely stream the data. I mean, of course it sounded like garbage because you can only pulse width modulate it so fast. So, but this is again, for example, some games sounded like quite amazing for people myself who didn't have a sound blaster until much later. And you can on a PC that otherwise only can beep pulse width modulate the PC speaker similar, just like some 3, 4, 6-bit resolution, or not amazing. Let's see how amazing we can sound this. And again, if we want it more fancy, I can hook up an I2S deck there of my board there on the shelves anyway. But for today, let's learn something. In the long term, where do I want to go with this? I want to make some small clone or similar implementation of an Yamaha OPL1-3. Of course, I will not implement a full one, but full one meaning I will not copy all the features, but some features, so the OPL2-3 as used in Adlib, Sound Blaster, and other Sharp and like NES and whatnot. And so what this is doing is this allows to run some operators here, some FM synthesis, a couple of those to have multiple voices, and program this with some attack, something, sustain, release, whatever, and to have some relatively somewhat naturally sounding tone. And so in the long term, like in a week or two, I would want to have something like this in the FPGA, just to show you where we are going. And this OPL2 or 3 or other similar Yamaha and similar circuits here, OPL, they allow basically to have like a sine wave, or later ones a rectangular sawtooth. They also have some picture here somewhere, and I thought at least they have somewhere. And later we want to do this here, some beeping nonsense of Adlib, Yamaha, OPL2, kind of, sort of, whatsoever. But for now, let's take a look. So what I've done here already, I hooked this up already to pin 4 on the PMod 2, a second, I think 1A, 1B, and PMod 2. This are signals directly going to the FPGA. This is where the LEDs are hooked up at, and the buttons. So right now I use button whatever, it doesn't matter, pin 4 on the PMod, and I think it's going to FPGA 19. We could actually check this here in something of Icebreaker PCF, and so PMod, that is so PMod 2, pin 4 is pin 19 on the FPGA on the IS40, where usually the button 2 is connected, so whatever, so don't press a button now. And this is where I directly hooked up the digital scope here. And what you see here already, so how does it work? We have a frequency of Lua computation fame here. So we have 12 megahertz is the base clock of our whole FPGA system here. 1, 2, 3, 1, 2, 3, I think like that. And if we divide this, so we maybe want something like CD quality, that would be something of that, 270 something, whatever, not amazing. But if we do here better than CD, like digital audio tape quality of 48K, that is 250, divider of 250. The only problem is we cannot easily, the power of 2 stuff you can easily divide, just shift around a little bit, so it's not easy to do just 250. But when we divide this by, for example, 256, for example, we could theoretically run this with a super simple, directly driven from the main FPGA clock frequency at 46875 whatever megahertz, or alternatively maybe we can also actually run it directly with 48K, but then not using a divider, but maybe comparing, like counting the clock and comparing this. We will see in a later episode. So for this to get started here, I already drafted here some notes. Also what other stuff, scrolling here, mouse wheel. So PC speaker can only do 1 square wave, that is why it sounds so, at least was it square wave, I think. Anyway, I hope my notes are correct, 2 levels off and on. PC Junior Tandy 1K also could do 3 square waves with 16 levels and some noise channel, already somewhat better. And then OPL2, so OPL2 from first Adlib cards and other cards in this area could do 9 channels with 2 oscillators, or minus, so oscillators meaning sine, I think in OPL, maybe OPL1 could only do sine or something, maybe OPL2 added like 4, or maybe, wait a second, right, maybe this OPL and OPL2 could only do sine waves. 2 oscillators, meaning you can combine them, like invert and flip and add and such. And the OPL3 of Adlib Gold, or what it was, and later Sound Blaster revisions, they had 18 channels, so double those channels, simple stereo for all left and all right, previous were all mono, and 4 new waveforms like sawtooth, rectangular, square and such. Here's just some addresses in I/O space. Of course, we also want to program this later from the RISC-V. So in a week or two, we will have video output and sound, hopefully. So we will have some registers, of course. PC I/O space here is 388 for AdLib compatible, and PC Junior 10-year apparently I/O port C0 to C8 or something. Here's these two nice diagrams I found in the web. So as I said, 12 megahertz divided by 250. So let's do this. For this, I have here already this Verilog file that is running right now. So this is the base we are starting off, and you see here we will have, this is I copied from the NES emulator, so that is, I'm using the same pin as the NES emulator that someone else has done already, pin 4 to pin 19 on the FPGA. And of course I started this as a module, so we have here module audio, clock and DSD for direct stream digital, our glorified, amazing direct stream digital. And to wire this up, this is of course in the test because the whole system takes so long to synthesize. So where is my no, it's not this. Oh, maybe top V. So this is the super simple test. That's not the full RISC-V PicoSoc with the early drafting. And to use this module, we include this, and then audio module here, we wire this here as paired to the system, and video PLL here, the main clock. So in input clock and output the direct stream digital to the P-mod2 pin 4. That is where the scope probe is attached there. And we can, let's take a look. So for example, I already oversampled this here with 250 just for the quick test of it. We just increment here the address right now. But basically this works like this. So the DSD is the output. So for always positive edge on clocks, these are the 12 megahertz. Of course you could scale it to whatever with a PLL, whatever frequency, or custom divide it in some way. And so clock, I increment here some counter. Later we will see how we implement this. Just wanted to give you some overview how this works in theory. Let's, for the simplicity for you to show you this, we have V here, some register V, and we increment this. Let's change this back to V, and here, like in C array, addresses is Verilog for register V bit 0 to the non-blocking assignment here to the direct stream digital. So let's synthesize this. I hope actually no files need saving. So this is right now synthesizing in quite a minute. So what this is doing is we increment the counter with running with 12 megahertz, of course fully parallel, because this is certainly logic attached to the clock, so fully independently. There you see the difference. A CPU is just executing instruction for instruction, and all this logic is running here parallel independently on some clocks. So independently of our RISC-V core and the video core, we have this logic elements connected to the clock and running fully independently to that. And this is the outcome here of that. Let's take a look if we can make some sense out of this fine stuff. We could just hit the auto button, or we can manually scroll in here, and certainly before we hit auto, manually scroll in here. So this is here the signal, this good old-fashioned, poor, also cheapskating hexacode, don't delay, try hexacode today. Digital scope of scanner, reverse engineering, office supply fame. This is a signal, and to some of you this might already surprise you that this is not super amazing rectangular. This is just the output. If you look on some kind of clock here on such kind of systems, yeah, that's not fully square, obviously. And we basically incrementing, so we increment this and output the last bit. So right now this incrementing this counting with 12 megahertz, the digital scope here correctly counts this here for us as relatively precise 6 megahertz. So based on this, so this is getting back to what we wanted to do in this terms of direct stream digital stuff. We would have some output register, and every for each sample, so we have some sample between 0 and 255, for example, to keep it simple for a start. We would not output here this counted clock, obviously, but the value we compute in some form here, and as a short test. So for example, dividing this here further by 8, so counting this down just for a test to show you the signals. This is basically dividing this here further by 8. Actually, we could, to show course is better. So although you always need to take into account that because when we count and use the last bit, it is already divided by 2, because we alternate between 0 and 1. So 0, 1, 2, or 3, and so on. But the last bit in binary is already already dividing the clock by 2. So if we want to shift this down 8, which is dividing by 256, which is close to this oversampling frequency that maybe we want to achieve relatively closely, then because we already divide by 2 naturally by counting this, we only need to shift 7. So let's synthesize this. Unfortunately, this always takes a short moment to synthesize here, not too long though. And this is also why actually, so right now we synthesize the VGA design, so it's also outputting the HDMI signal here that we are not taking a look at right now. But now you see here this changed here with this reprogramming, and again still not square. Also, and by the way, not sure if this cable is just shitty. This high frequency stuff, either this high frequency stuff could be some interference of HDMI and FPGA clock goodness, not sure, or it could be that this cables are also garbage. But anyway, so let's change here the time division scale here, and then you see when this can, wait a second, 8. Where do we have? Let me think. Okay, so then slide synco. Anyway, by the way, not really sure why we do have so many. Also, it could also be I have the ground plane on the USB. I'm not sure. I actually should have checked the schematic. It doesn't really matter too much. Of course, when we connect a speaker or a headphone, and we should actually use the ground pin. Just that I couldn't easily connect the ground pin there. That's why, theoretically. But anyway. So, oops. So now we run. Why is this 50? Why is this counting so? Why is this 60 kilohertz? What am I doing there? Anyway, slightly more of 260. What is even 12 megahertz? Divided by 200, it should be 46, but somehow it isn't. Maybe because it's somehow not really sure what's up with the 60 there right now. Anyway, there you see here the concept that we're working with. I'm really slightly irritated by all the noise on this line. Whatever is, yeah. Anyway, so what we would want to do next is to maybe, so how do we do this? We could actually just have this in some 8-bit register. So basically we want to, for example, to send out some bit pattern. Let's try that. Let's for a start, so we are counting V. If we make V2 the output here, we could make this 8 bits. For some output, define some test pattern here of 8 bits, binary of just to count this, so 4 ones, 3 zeros, and then, does it make sense? 1, 2, 3, 4, 5, 6, 7, 8, not really 1, 2, 3, yeah, right, that is one too many, maybe. 1, 2, 3, right, so that would be 8. If we clock out 8 bits, so for example, how we could do this is to output the high bit of this here. I'll use this like a shift register. Output always the high bit, so given that this would be the pattern of direct stream digital here, of this kind of pattern, 3 ones, 3 zeros, a 1 and a 0 here, just for an example proof of concept. We could assign here the 7th bit, the high bit of this, and then also for, yeah, by the, not overwrite this, but for a, actually, I also need to load it, yeah, to have, so, okay, one step at a time for you to learn the most. So to have this here shifted, we could shift this here. Well, either I wonder, okay, we could probably, let's see if we can index it with, if we count this, we could simply index this bit most likely. Let's hope that works. Index this with a bit 7 to 0, counting from, actually this would be, that would make it reversed. Okay, 8 minus, generating quite some unnecessary logic. But otherwise, so if we use it as a shift register, this V2, we would need to reload this. So you could also shift this, probably this should work, shift this one to right, to the left. But then we would need to reload this. Then we would shift all the values. After shifting them to the left, we would lose all the values. So we would also eventually need to reload this. So to avoid reloading, let's try this. Probably should work. 8 minus this count of, oh, wait a second, this is also not correct. We only need 8, so that is 1, 2, 1, 1, 2, 3, 4, 5, 6, 7, 3 bit for 8. That should probably work. So this, the difference is, instead of shifting this away into the digital nirvana and the bits falling out of our PCB there or so, using this to index this bit, that probably should work. Let's see if this synthesizes. What unexpected 4, 6, what have we done now? 4, 6, there, probably something like that. Let's see how many logic elements it is using. So it's as a next step, when this works, outputting is a direct stream digital pulse with modulation pattern that we want to see here. Let's see, does this maybe, hello? There was freeze, acquire, there was stop run, auto set, acquire, here was save recall. Where would be the, didn't help erase, here run stop. So does this, could actually look like this is legit when we compare this to our intended patterns. There you see also, yeah, digital stuff, not always as we previously determined, and not a super nice square wave with some ringing and overshooting, and certainly some higher frequency limits there. So this should be 3 zeros, 1, 2, 3. Then actually 3, did we, maybe we, actually I slightly wonder what is the heck going on with that though. Why is this signal that so much noise in the signal? Because should probably not have. Does this make sense? Bit 8 we assign here is a bit, so basically using this as an address. 8 minus, looks like this should work. And we had some, really wondering why this signal is that garbage right now. Or maybe because zooming in for some strange sampling reason. I mean 3, 1 does not look entirely how I want it. But the tendency is at least there. slightly wonder. 3-1 LV. Maybe we make this as a test 4, 1, 2, 3, 4, and then 4, 2, 1. Anyway, so next actually doing the rest of the OPL is actually more tricky because all the envelope generation is actually pretty tricky in hardware. This is envelope generation, meaning you have a MIDI node you have some node on all your voices and have all the attack, decay, sustain, release stuff here. So we would need to generate this. Certainly we would do this with some having this on the timer and having some increment values of probably directly programming some increment and decrement values so that we just have some level register for each of the voices running, and then with this pre-programmed increment steps modify that. So does this make more sense now? Actually, by the way, do I have a... where was the... Here is it. Oops. Someone not amazing. Let's see, we have, it should be 4 on, 4, let's see, what did we had here? 4, 2, 4, 2, I slightly wonder if this is reversed for some reason, not that it should be, but maybe we try, but they also see the flexibility. If this would be connected to a RISC-V core, we could easily modify this here. If it's not connected to some programmable CPU-like thing, then each time we want to do something, we need to resynthesize this here, and that takes shortly. So right now this should be all 0. Let's also probably run this. Yeah, maybe we really have so much noise there on this level of the FPGA pins, which makes it like that. Slightly. Oh, wait a second. Ah, we had invert on, that explains the thing. Darn it. Yeah. Good old-fashioned scope stuff. So right now the signal should be 0. Also, yeah, this invert certainly there you see, if you always double, triple check and everything, if it's reverted, then certainly that explains a thing. Should be 4 bits on, 2 bits off, on, off. So that makes more sense. 4 bits on. Again with a high resolution, but somehow we have too much noise there. 4 bits on, 1, 2, 3, 4, 2 bits off, 1 off. Now it makes more sense, it isn't inverted anymore. Surprise, surprise. So to use this, so this means we can already output some pattern here, this pulse. So this is basically the pulse width modulation. We can also name this nicely, pulse width modulation. And we had this F2, so pulse width modulation. I also should probably show you that. And yeah, so recommendation, always name this stuff in some usable form. And what we would need to do next, I mean, beside hooking up the speaker and headphone and some, I mean, basically the headphone already acts like a low pass naturally, but besides that, we could add some capacitor resistor there to make some nice low pass. Next we would need, so now we can output the pattern. Next we could also look at how this looks. Of course, a square wave, for example, so if we have this 44, I mean, of course this sampling frequency is bonkers. We don't need such a high frequency, maybe later we need to check what sounds the best on this poor man's DAC. So next we would need to have some generators for this. We would also, by the way, for this generators envelope generator, envelope meaning this stuff here, and then some frequency based on this. Of course, some stuff is easy. So, which by the way, what did I move here? Did I? Okay, copy this. So this means we would have some counters. Also, I would probably suggest to model this first in some program like MATLAB or GNU Octave or something like that, because certainly it is certainly more scientific and less error prone and less trial and error if you model your algorithm of envelope generation and frequency generation. So basically this is some envelope. What we want is the output here in 8-bit, so or even 16-bit or whatever later, so to speak. The output should be our envelope. Envelope is this waveform here of that. So if we have this between 0 and 1, whatever the scaling might be, like 8 or 16-bit, whatever. So envelope multiplied with our frequency. So this is just the volume at a given time, and additionally we would have some frequency. The frequency coming from some generator. So this might either be a sine. The sine actually is not the most easy. We would need to approximate this with something like, I think the OPL, not really sure if they write this here in this. I think this OPL used some read-only memory to approximate sines. Do they not? Not even, maybe, oh, wait a second, this is not OCR, darn it. Yeah, here's so phase generator, so that would be a phase of the FM sound, that is what I meant. So we could also mean this, not frequency, but phase. So that would be envelope multiplied by phase, yeah, envelope generator. So this would be envelope generator multiplied by phase generator, and then also some additional modulation here, like vibrato, but obviously we do not bother about this. First we want to get some beeping tone out of there. Last but not least, if we want to mix more than one operator there, we need to accumulate them all together. So the accumulator is used to accumulate each sound, sampling time 50 kilohertz in order to convert data to match the DA converter, which I'm surprised it's running at 50 kilohertz there, the old-fashioned stuff. So first to make this simple, as I said, generating the phase of the sine, of course on a full-blown x86 or PowerPC or whatever, that would just be sine on some floating point value. Oh, this is funny that this is highlighting it like this fun stuff, Emacs terms here. So sine of sample of time here of V or something. Of course we don't have sine here in the FPGA, so we would need to approximate this. Usually you do this with some tables, so you have here some ROM area of initialized static data of some sine wave and approximate this. It certainly takes quite some 100 or whatsoever logic elements. So given that, initially, to make our life easy, we would support here some square wave of Z frame here. Looking that, and also then easy to do is all kinds of variations of where would even wait a second, backslash there. So that would be some sawtooth stuff of all the stuff that is easy to do without some fancy floating point and sine math. Sawtooth, if you didn't, sawtooth phase wave, let's see if we are here. So something of that sort, or like sawtooth or triangle of that frame here, either that or that stuff. That's certainly super easy, just some incrementing stuff, and certainly obviously much easier just to increment some value than interpolating some sine wave out of some ROM area. So that's basically the introduction of how to do here this fun stuff. We could continue a little bit hooking up here, but the thing is, if I now get out some more electronic stuff and hook up here some headphone, to get some sound out. Of course, you should not really do that too much. Of course, theoretically, we should also have here some driver, not to connect this directly to the FPGA. The NES emulator people said it's fine. They didn't burn the FPGA yet, but with a resistor probably shouldn't overload and stuff. So probably I will solder and resistor, maybe also break off this PMOD there. This side one is there to break off. So that is something. Breaks this off, plugs this in there. Have also, yeah, theoretically we could certainly zoom into there that you better see. So yeah, breaks this break off pad off here, and then plug in there some resistor, capacitor, and headphone jack. Then our RX32 system is already more amazing than an iPhone with a headphone jack. As usual, leave me in the comments below if you have questions, tips, and other fun stuff. So if so, for example, what we could do maybe as the last thing here to make this a little bit fancy, let's generate conclude here this. We have, let's see, so this is counting the bits through. If we want to do something, let's try to generate here some sawtooth. That would be, by the way, I wonder if we can, theoretically, we can, instead of dividing, because as you see, we cannot easily divide by 250, which would exactly be 48K. We could probably increment this, and again, as we learned previously, this is a non-blocking assignment, meaning it is, the logic is generated in such a way that V is sampled at the beginning of the positive edge clock pulse here, and the new value V is assigned to the buffered flip-flops there at the end of this clock. So that not only this works, so this works, otherwise it would short circuit assign this here anyway, but in some way, so to say. But the other thing is, this also means we should keep into account that if we write here code like if V equals oversample, for example, that probably should work. I hope this local param stuff here works like that. Whereas even our counting stuff is V, also probably, let's name this count just to be a little bit more, get people to use more useful variable names than just X, Y, Z, V, I, J, K. So if our count here, also this count, if our count equals this oversample thing, then wait a second. Let's begin. Oops, begin. I think begin end. The only thing is we run. Too much mixing all the programming languages. Yeah, this needs brackets here. I think I'm not writing Lua today. Just that this count is outputting. Yeah, let's keep it simple. Otherwise, it is slightly out of sync. Let's not yet do that. Let's do if to make it simple, and otherwise we are out of sync between clocking out our pulse width modulated stuff and incrementing the clock. So if this count equals 0, for example, then load the new value, which also, so if we make this count just 8-bit to count from 0 to 255, then load here the new value, which, by the way, let's synchronize this a little bit so this works. So sample this in the beginning, assign, so maybe we make this 255 for the simple reason that to assign this, because the new value, like the new computed value for our output, our PWM, would be the next clock. So if to keep this in mind, also if you are more into Verilog and stuff, let me know how to best do this kind of stuff. So if we to do the synchronized, like not to lose 1 bit in imprecision and stuff in off by 1 terms, do this here at the end of this count just before the overflow, and increment this. So for example, PWM plus 1. This would make a simple sawtooth here, always incrementing this with the frequency of our clock divided over sampling 1255 right now. I mean, right now we are not using this yet, maybe comment it out for avoiding confusion. Unexpected something in 51. Out, right, this was just illustration purposes only. Also, why did I remove this? Not really sure when I removed this. Come on, begin, end, what have I done now? 60. Also best with semicolon. Too much mixing all this. So this should generate a sawtooth in terms of incrementing this here in a linear fashion, this pulse width modulated stuff, and clocking this out here in 256 clocks. Let's see, actually we should run this. It's a little bit unfortunate, so as you see, this is now, the problem is it's not a logic analyzer. I mean, we can sample this, save and recall theoretically, but let's not overcomplicate this today. It's probably enough to illustrate that now, as also probably should zoom this in. Now this obviously is clocking very fast, and if we would actually not be probably, yeah, there you see the difference between not having this properly low pass filtered. If we low pass filter this with resistor and capacitor, then we would have already our nice signal here. Should we? But now you see it's counting very fast between no bit set to all the bits set. Of course, we also need to have some assignment there to generate the correct waveform. Right now we only count the bits through. Later we need to have a mapping of pulse width modulation of this value to how many bits are set in this. But just to illustrate this here. So questions to the audience. So right now this probably is already all the basics here for this video. Let me think, we right now, yeah, maybe we do the other stuff. So, but basically this is how the easiest form of sawtooth generation, although maybe the easiest is a square. And certainly with this we could also stream PCM data, probably upsetting some audio fields, having some PCM samples in our RISC-V core in the flash or whatever, or runtime generated, and streaming them here into the registers and clocking them out, having some speech output or explosion kind of sound output. But that is then for the next videos. Otherwise, again, we will have here some registers similar to the VGA code. The VGA code, of course, if you have not seen this previous long video, Pico, SOC, VGA stuff here. And similar to this, we will have some bus interface to the Pico RISC-V, Pico SOC here, and writing the registers, similar to the OPL here of Yamaha fame, having this Yamaha. So this has some registers, as you see here somewhere. So similar to this, registers of Adlib OPL2-3 fame. Some timers and stuff that probably is used in a similar fashion to our timer. And then here's this attack rate, decay rate, sustain rate, release rate, and frequency and stuff. And similar to this, we would have a couple of operators that we would program to generate what kind of signal we want, accumulating those and outputting them here, pulse width modulated here on this direct stream digital. I hope you learned something and find this helpful of how hardware works here on the digital levels and generating some audio signals here in PCM to direct stream digital, poor man's or audiophile, depending on from which way you look here, and learn something in the process also how sound hardware works on your PC or Amiga stuff or Commodore stuff. Let's see what else do we have here. Quite some comments that scrolled by in the meantime. How long are we even? 0 drop frames. Here live from this AMD Ryzen previous video. 50 minutes, probably long enough for this introduction. So Mr. Bonk wants to put a PDF of his Sax ICER. That is also amazing. Again, welcome everyone and thanks for watching. I hope you learned something. Sax emulator, amazing stuff. It's a link to something like on the so they use something like that on the Raspberry Pi. Not the best audio quality, but it works. I thought, does the Raspberry Pi not have some I2S interface? I thought, or other stuff, but yeah. Then let's see only the links there, and they could go GitLab. So Sax is a real thing. So yeah, it will not be a full AdLib clone. Not only do I not want to get sued from Yamaha after the decades or two, so this will be similar to AdLib. So we will not. So neither will we implement this register compatible nor feature compatible. It basically is also limited because we need to have this on the same ICE right now anyway. Later, because of course can use any other FPGA, but right now we want to run this together with the Pico RISC-V, so we don't have so many logic gates left right now. This design is using, let's see, also this is using together with the VGA core. So this is using not too many 400, so probably only some 50 or so. Hopefully we could actually, so this is 451. The easy way to count this is simply to comment this out. Audio, so if we just comment this out and resynthesize this, we should, so 451, let's see how many we get now. Yeah, so 50, so 40, so right now the simple pulse width modulation stuff is using 42, I think, logic elements there. Of course, later we will use more, but there you see how quickly this stuff up. Just a couple of counters. Let's comment this in again. And also, by the way, this will be also how we add this to our Pico sock. So alongside to VGA, we will have this audio, and we also need some logic elements there left for keyboard and mouse. So can't use all of them for. So this will be just like, it will be similar to Tandy or so. Maybe, yeah, so I hope so. This will be somewhere between Tandy, PC Junior, Tandy 1000 stuff here, and which only could do 3 square waves. So we will probably have something of, I don't know, depending on how many logic, so 3 square waves with configurable waveform. So this will be like a third of an OPL or something of that sort. Let's see. But again, the nice thing of an FPGA, if we just take a larger one, we can just have this in a module and instantiate it like 8 times, and then you are flexible and may even make this a configuration parameter of how many of those oscillating operators you want to instantiate. So the FPGA is the limit, and if you have a large one and stuff, you can just instantiate plenty of them. So Christian writes assembler in CSS favorite language, reminds him on 68, 65, 68 something, upload precompiled PDF, managed to hash MD5 after a lot of keyboard meshing, fun processor. Happy that you enjoy it. What else do we have there? Core RISC. This RISC-V will be powerful enough to run some voice over IP app and have some pure open source hardware software communication device. Maybe, I'm not sure how fast, but theoretically something of that sort. Sorry. But certainly without Linux, right? This would be firmware only, so for sure it should be possible to, I would think it should be possible to do this like firmware only, bare metal, without Linux, obviously. Some voice over IP. We certainly, so in some weeks or months time, we certainly have an example of Tetris or Pac-Man running on there, just for the homebrew fun of that. And Mr. Bonk asked when I'm going to learn sax assembly. Maybe never, because I'm actually relatively busy. Sorry to say this, as much as I appreciate your effort. I'm a little bit busy with this stuff, so I'm more learning RISC-V assembly and stuff that people use here nowadays. So yeah, that's it for today. If you have found here one error already, so of course this assignment here is not correct. In terms of incrementing this, we would need to have here some assignment of pulse width modulating. So let's see, we would need to have something of converting, because this is here the value we want. This is not entirely correct in terms of, basically we have 8 bits. The question is slightly, I probably need to read some more theory about this direct stream digital, because what we actually need to map, we need to map 0. 0 needs to map to all bits 0. 1, 2, 3, 4, 5, 6, 7, 8. And 1, which is our equivalent of 255 or whatever, would need to map all bits high. All bits high. And so something of that we need. Either in some lookup table or some logic, and everything in between. So for example, 128 would be, I don't know how we implement this alternating, not sure what, but this is probably not the best, because we also need here something of, like, you see how amazing this super audio CD stuff is, right? If we have here some 64, this should be like, not like half off and on in terms of this pulse width modulation stuff. So I probably need to shortly read into the theory how to map this the best. And then of course, so basically the higher the value, the more bits set for a longer time, 127 or whatever that is, to some all bits set except some not really sure how we would want to map this, but that is in general the idea. Anyway, I hope you learned something, and next I probably finish this mapping here off camera. Probably a little bit too boring to, you see already, just the basics 1 hour or so, and better finish more of those details and then connect the stuff and present you the final result if there is some nice stuff hearable and audible. And yeah, if you have comments, tips, tricks and other fun stuff, leave it in the comments below. Otherwise, thanks for watching, hope to see you soon, and I hope to learn something. I hope you learn something, so it's probably not enough coffee today.